Thanks for being here for lecture 5 of CS230. Today we have the chance to host a guest speaker, Pranav Rajpurkar, who's a PhD student in computer science advised by Professor Andrew Ng and Professor Percy Liang. So Pranav is working on AI and high-impact projects specifically related to healthcare and natural language processing. And today he's going to present an overview of AI for healthcare, and he's going to dig into some projects he has led through case studies. So don't hesitate to interact. I think we have a lot to learn from Pranav. And he's really an industry expert for AI for healthcare. And I let you the mic, Pranav. Thanks for being here.
Thanks, Kian. Thanks for inviting me. Can you hear me at the back? Is the mic on? All right, fantastic. Well, really glad to be here. So I want to cover 3 things today. The first is give you a sort of broad overview of what AI applications in healthcare look like. The second is bring you 3 case studies from the lab that I'm in as demonstrations of AI in healthcare research. And then finally, some ways that you can get involved if you're interested in applying AI to high-impact problems in healthcare, or if you're from a healthcare background as well. Let's start with the first. So one way we can decompose the kinds of things AI can do in healthcare is by trying to formulate levels of questions that we can ask from data. At the lowest level are what are descriptive questions. Here we're really trying to get at what happened. Then there are diagnostic questions where we're asking, why did it happen? If a patient had chest pains, I took their x-ray, what does that chest x-ray show? If they have palpitations, what does their ECG show? Then there are predictive problems. Here I care about asking about the future, what's going to happen in the next 6 months. And then at the highest level are prescriptive problems. Here I'm really trying to ask, okay, I know this is the patient, this is the symptoms they're coming in with, this is how their trajectory will look like in terms of things that may happen that they're at risk of, what should I do? And this is the real action point. And that's, I would say, the gold mine, but to get there requires a lot of data and a lot of steps, and we'll talk a little bit more about that. So in CS230, you're all well aware of the paradigm shift of deep learning. And if we look at machine learning in healthcare literature, we see that there's a very similar pattern, is that we had this feature extraction engineer who was responsible for getting from the input to a set of features that a classifier can understand. And the deep learning paradigm is to combine feature extraction and the classification into one step by automatically extracting features, which is cool. Here's what I think will be the next paradigm shift for AI in healthcare, but also more generally, is we still have a deep learning engineer up here. That's you, that's me. That are designing the networks, that are making decisions like a convolutional neural network is the best architecture for this problem, the specific type of architecture. There's an RNN, CNN, and whatever NN you can throw on there. But what if we could just replace out the ML engineer as well? And I find this quite funny because everyone, in AI for healthcare, a question that I get asked a lot is, are we going to replace doctors with all these AI solutions? And nobody actually realizes that we might replace machine learning engineers faster than we might replace doctors if this is to be the case. And a lot of research is developing algorithms that can automatically learn architectures, some of which you might go through in this class. Great. So that's the general overview. Now I want to talk about 3 case studies in the lab of AI being applied to different problems. And because healthcare is so broad, I thought I'd focus in on one narrow vertical and let us go deep on that, and that's medical imaging. So I've chosen three problems, and one of them's a 1D problem, the second is a 2D problem, and the third is a 3D problem. So I thought we could walk through all the different kinds of data here. So this is some work that was done early last year in the lab, where we showed that we were able to detect arrhythmias at the level of cardiologists. So arrhythmias are an important problem, affect millions of people. This has especially come to light recently with devices like the Apple Watch, which now have a ECG monitoring. The thing about this is that sometimes you might have symptoms and know that you have arrhythmias, but other times you may not have symptoms and still have arrhythmias that can be addressed if you were to do an ECG. And the ECG test is basically showing the heart's electrical activity over time. The electrodes are attached to the skin, safe tests, and it takes over a few minutes. And this is what it looks like when you're hooked up to all the different electrodes. So this test is often done for a few minutes in the hospital. And the finding is basically that in a few minutes, you can't really capture a person's abnormal heart rhythms. So let's send them home for 24 to 48 hours with a Holter monitor, and let's see what we can find. There are more recent devices, such as the Zio patch, which let patients be monitored for up to 2 weeks, and it's quite convenient. You can use it in the shower or while you're sleeping, so you really can capture a lot of what's happening in the heart's ECG activity. But if we look at the amount of data that's generated in 2 weeks, it's 1.6 million heartbeats. That's a lot. And there are very few doctors who'd be willing to go through 2 weeks of ECG reading for each of their patients. And this really motivates why we need automated interpretation here. But automated detection comes with its challenges. One of them is, you have in the hospital several electrodes. And in more recent devices, we have just one. And the way one can think of several electrodes is sort of the electrical activity of the heart is 3D. And each one of the electrodes is giving a different 2D perspective into the 3D perspective. But now that we have only one lead, we only have one of these perspectives available. And the second one is that the differences between the heart rhythms are very subtle. This is what a cardiac cycle looks like. And when we're looking at arrhythmias or abnormal heart rhythms, one's going to look at the substructures within the cycle and then the structure between cycles as well. And the differences are quite subtle. So when we started working on this problem, maybe I should share this story. So we started working on this problem, and then it was me, my collaborator Ani, and Professor Ng. And one of the things that he mentioned we should do, he said, let's just go out and read ECG books, and let's do the exercises. And if you're in med school, there are these books where you can learn about ECG interpretation, and then there are several exercises that you can do to test yourselves. So I went to the med school library. They have those hand crank shelves at the bottom, so you have to move them and then grab my book. And then we went for 2 weeks and did go through 2 books and learn ECG interpretation, and it was pretty challenging. And if we looked at previous literature to this, I think they were sort of drawing upon some domain knowledge here, in that here we're looking at waves. How can we extract specific features from waves that doctors are also looking at? So there was a lot of feature engineering going on, and if you're familiar with wavelet transforms, they were the most common approach with a lot of sort of like different mother wavelets, et cetera, pre-processing bandpass filters. So everything you can imagine doing with signals was done. And then you fed it into your SVM and you called it a day. Now with deep learning, we can change things up a bit. So on the left, we have an ECG signal. And on the right is just 3 heart rhythms. We're going to call them A, B, and C. And we're going to learn the mapping to go straight from the input to the output. And here's how we're going to break it out. We're going to say that every label labels the same amount of the signal. So if we had 4 labels, then the ECG would be split into these 4, sort of this rhythm is labeling this part. And then we're going to use a deep neural network. So we built a 1D convolutional neural network, which runs over the time dimension of the input. Because remember, we're getting one scalar over time. And then this architecture is 34 layers deep. So I thought I'd talk a little bit about the architecture. Have you seen ResNets before? OK. So should I go into this?
You can go. They're going to learn about ResNets next week. OK, cool. Here's my 1-minute spiel of ResNet then, is that you're going deeper in terms of the number of layers that you're having in a network. You should be able to represent a larger set of functions. But when we look at the training error for these very deep networks, what we find is that it's worse than a smaller network. Now, this is not the validation error. This is the training error. That means even with the ability to represent a more complex function, we aren't able to represent the training data. So the motivating idea of residual networks is to say, hey, let's add shortcuts within the network so as to minimize the distance from the error signal to each of my layers. This is just math to say the same thing. So further work on ResNet showed that, OK, we have the shortcut connection. How should we make information flow through it the best? And the finding was basically that anything you add to the shortcut, to the highway, think of these as stop signs or signals on a highway. And it's basically saying the fastest way on the highway is to not have anything but addition on it. And then there were a few advancements on top of that, like adding dropout and increasing the number of filters in the convolutional neural network that we also added to this network. OK, so that's the convolutional neural network. Let's talk a little bit about data. So one thing that was cool about this project was that we got to partner up with a startup that manufactures these hardware patches, and we got data off of patients who were wearing these patches for up to 2 weeks. And this was from around 30,000 patients. And this is 600 times bigger than the largest data set that was out there before. And for each of these ECG signals, what happens is that each of them is annotated by a clinical ECG expert who says, here's where rhythm A starts and here's where it ends. So let's mark the whole ECG that way. Obviously very time intensive, but a good data source. And then we had a test set as well. And here we use a committee of cardiologists. So they'd get together, sit in a room, and decide, OK, we disagree on the specific point. Let's try to discuss which one of us is right or what this rhythm actually is. So they arrive at a ground truth after discussion. And then we can, of course, test cardiologists as well. And the way we do this is we have them do it individually. So this is not the same set that did the ground truth. There's a different set of cardiologists coming in, one at a time. You tell me what's going on here, and we're going to test you. So when we compared the performance of our algorithm to cardiologists, we found that we were able to surpass them on the F1 metric. So this is precision and recall. And when we looked at where the mistakes were made, we can see that sort of the biggest mistake was between distinguishing 2 rhythms, which look very, very similar, but actually don't have a difference in treatment. Here's another case where the model is not making a mistake, which the experts are making. And turns out this is a costly mistake.
This is saying a benign heart rhythm, or what experts thought was a benign heart rhythm, was actually a pretty serious one. So that's one beauty of automation, is that we're able to catch these misdiagnoses. Here are 3 heart blocks, which are clinically relevant to catch, on which the model outperforms the experts. And on atrial fibrillation, which is probably the most common serious arrhythmia, the same holds. So one of the things that's neat about this application, and a lot of applications in healthcare, is what automation with deep learning, machine learning enables is for us to be able to continuously monitor patients. And this is not something we've been able to do before, so a lot of even science of understanding how patients' risk factors, what they are or how they change, hasn't been done before. And this is an exciting opportunity to be able to advance science as well. And the Apple Watch has recently released their ECG monitoring. And it'll be exciting to see what new things we can find out about the health of our hearts from these inventions. Okay, so that was our first case. Yeah, question?
How big of a problem did you find the data privacy issue to be in collecting that humongous data set, which is awesome, by the way?
Yeah, so I'll repeat the question. How difficult was it to sort of deal with data privacy and sort of keep patients' information private? So in this case, we had completely de-identified data. So it was just someone's ECG signal without any extra information about their clinical records or anything like that. So it's very de-identified.
Sorry, I guess I meant to ask that. How did you get the approval for that, and were there problems in getting the approval? Because there's a lot of huge data privacy concerns. So did you have to get it signed off by some federal authority, or what are the obstacles in getting that to be there?
Oh, sure. And I think we can take this question offline as well. But one of the beauties of working at Stanford is that there's a lot of industry research collaborations, and we have great infrastructure to be able to work with that. Yeah. So which brings me on to my second case study. Sorry, yeah, go for it.
What's the gold standard for determining whether this patient has arrhythmia or not? It feels like you are using the expert cardiologist as your gold standard, and you are also comparing with their performance. So how do you actually define the gold standard?
That's a good question. So just to repeat the question, how did we define the gold standard when we have experts setting the gold standard? So here's how we did it. So one way to come up with the gold standard is to say, okay, if we looked at what a consensus would say, what would they say? And so we got 3 cardiologists in a room to set the gold standard. And then to compare the performance of experts, these were individuals who were separate from those groups of cardiologists who sat in another room and said what they thought of the ECG signals. That way there's some disagreement where the gold standard is set by the committee. Great. So here we looked at how we can detect pneumonia off of chest x-rays. So pneumonia is an infection that affects millions in the US. Its big global burden is actually in kids. So that's where it's really useful to be able to detect that automatically and well. So to detect pneumonia, there's a chest x-ray exam. And chest x-rays are the most common imaging procedure with 2 billion chest x-rays done per year. And the way abnormalities are detected in chest x-rays is they present as areas of increased density. So where things should appear dark, they appear brighter, or vice versa. And here's what characteristically pneumonia looks like, where it's like a fluffy cloud. But this is an oversimplification, of course, because Pneumonia is when the alveoli fill up with pus, but the alveoli can fill up with a lot of other things as well, which lead to very different interpretations and diagnoses for the patients and treatment for the patient. So it's quite confusing, which is why radiologists train for years to be able to do this. The setup is we'll take an input image of someone's chest X-ray and output the binary label 0 or 1, which indicates the presence or the absence of pneumonia. And here we use a 2D convolutional neural network, which is pre-trained on ImageNet. Okay, so we looked at shortcut connections earlier, and DenseNets had this idea to take shortcut connections to the extreme. It says, what happens if we connect every layer to every other layer instead of just connecting sort of one, instead of having just one shortcut, which is what ResNet had. And DenseNet beat the previous state of the art and has generally lower error and fewer parameters on the ImageNet challenge. So that's what we used. For the data set, when we started working on this project, which was around October of last year, there was this large data set that was released by the NIH of 100,000 chest X-rays. And this was the largest public data set at the time. And here, each X-ray is annotated with up to 14 different pathologies. And the way this annotation works is there's an NLP system which reads a report and then outputs for each of several pathologies, whether there is a mention, whether there is a negation, like not pneumonia, for instance, and then annotates accordingly. And then for a test set, we had 4 radiologists here at Stanford independently annotate and tell us what they thought was going on in those X-rays. So one of the questions that comes up often in medical imaging is we have a model, we have several experts, but we don't really have a ground truth. And we don't have a ground truth for several reasons sometimes. One of them is just that it's difficult to tell whether someone had pneumonia or not without additional information like their clinical record, or even once you gave them antibiotics, did they get treated? So really, one way to evaluate whether a model is better than a radiologist or doing as well as a radiologist is by saying, do they agree with other experts similarly? So that's what we use here. That's the idea. We say, okay, let's have one of the radiologists be the prediction model we're evaluating, and let's set another radiologist to be ground truth. And now we're going to compute the F1 score once, change the ground truth, do it the second time, change it again, third, and then also use the model as the ground truth and do it again. And we can use a very symmetric evaluation scheme, but this time having the model be evaluated against each of the 4 experts. So we do that, and then we get a score for both of them. Well, for all of the experts and for the model. And we showed in our work that we were able to do better than the average radiologist at this task. 2 ways to extend this in the future is to be able to look at patient history as well and look at lateral radiographs and be able to improve upon this diagnosis. At the time at which we released our work on all 14 pathologies, we were able to outperform the previous state of the art. Okay, so model interpretation. Model interpretation, yes, there's a question.
Go back to that slide that you had on future work. So, one more slide, please. Yeah. So, if you have pneumonia, you present it to the doctor, you have like fever, you're coughing, your ribs hurt, you're coughing too much, you can't sleep, all those other issues, that's not included in the model. So I think my question is that if you're going to a data set and you're trying to determine, does this person have pneumonia or not, like, that's one thing, but you don't, it's not that you just don't add that data, but you're not looking at other images. Let's say, does that person have cancer, or does that person have like other occlusions in the lung because they inhaled coal or asbestos? And so all those are images that you're not really looking at. So let's say in a tough situation, so the obvious situation doesn't really do you much good, right? But in a tough situation, if you get a patient that has a fever and is coughing violently, you don't know if it's cancer or pneumonia or black lung disease, then how do you get your algorithm to work in that condition? And also, if you're not including all those other cases, then it's not just that what's the use of it, but like, you know what I'm saying?
Yeah.
And so so I'm trying to keep it this technical, this is a technical class. Is there a neural network architecture that you would use to be able to solve problem number one? Is it multitask learning? Is it like?
Sure. Okay, so let me try to boil those sort of sets of questions down. So one is patients are coming in, we're not getting access to their clinical histories, so how are we able to make this determination at all? So one thing is that when we're training the algorithm, we're training the algorithm on pathologies extracted from radiology reports. And these radiology reports are written with understanding of full clinical history and understanding of sort of what the patient presented with in terms of symptoms as well. So we're training the model on these radiology reports, which had access to more information. And the second is that the utility of this is not as much in being able to compare a patient's x-rays day to day, as much as here is a new patient with a set of symptoms, and can we identify things from their chest x-rays? Which brings us to model interpretation. So if you were an end user for model, so when I was back in undergrad and I was in the lab, we were working on autonomous cars. And I thought about this a lot. How many of you have been in an autonomous car? How many of you would trust being in an autonomous car? All right, cool. Yeah, I thought about this as well. Would I trust being in an autonomous car? And I thought it'd be pretty sweet if the algorithm that was in the car would tell me whatever decision it was going to make in advance. I know that's not possible at high speeds, so that, just in case I disagreed with a particular decision, I could say, no, abort, and have the model sort of, remake its decision. And I think the same holds true in healthcare as well. The one advantage that happens in healthcare is rather than having to make decisions within seconds, like in the case of autonomous car, there is often a larger time frame, like minutes or hours, that we have. And here, it's useful to be able to inform the clinician that's treating the patient to say, hey, here's what my model thought and why. So here's the technique we use for that, class activation maps, which you may cover in another lecture. So I'll just leave it at saying that there are ways of being able to look at what parts of the image are most evident of a particular pathology to generate these heat maps. So here's a heat map that's generated for pneumonia. So this X-ray has pneumonia, and I can and the algorithm in red is able to highlight the areas where it thought was most problematic for that. Here's one in which it's able to do a collapsed right lung. Here's one in which it's able to find a small cancer. And here the goal is to be able to improve healthcare delivery, where in the developed world, one of the things that's useful for is to be able to prioritize the workflow, make sure the radiologists are getting to the patients most in need of care before ones whose x-rays look more normal. But the second part, which I'm quite excited about, is to increase the access of medical imaging expertise globally, where right now the World Health Organization estimates that about 2/3 of the world's population does not have access to diagnostics. And so we thought, hey, wouldn't it be cool if we just made an app that was able to allow users to upload images of their of X-rays and be able to give its diagnosis. So this is still in the works. So I'll show you what we've got running locally. And so here I'm presented with a screen that asks me to upload an X-ray. And so I have several X-rays here. And I'm going to pick the one that says cardiomegaly. So cardiomegaly refers to the enlargement of the heart. So I uploaded it. Now it's running. The model's running in the back end. And within a couple of seconds, it's outputted its diagnoses on the right. So you'll see the 14 pathologies that the model is trained on being listed. And then next to them, a bar. And at the top of this list is cardiomegaly, which is what this patient has. The heart is sort of extending out. And if I hover on cardiomegaly, I can see that the probability is displayed on there. And now we talked about interpretation. How do I believe that this model is actually looking at the heart rather than looking at something else? And so if I click on it, I get the class activation map for this, which shows that indeed it is focused on the heart to be able to, and is looking at the right thing. So I guess you can say the algorithm's heart's in the right place. Cool. But I thought, so this is an image that I got from the data set that we were using, NIH. But it's pretty cool if an algorithm is able to generalize to populations beyond. And so I thought what we'd do is we could just look up an image of cardiomegaly and download it and just see if our model is able to. This one looks pretty large. So does this. I don't want an annotated one. All right, that's good. So we can do that, save it, desktop. And now we can upload it here. And it's already redone its thing, and on the top is cardiomegaly once again. So it's able to generalize to, and there's the highlight. So it's able to generalize to populations beyond just the ones it was trained on. So I'm very excited by that. And what I got even more excited by is we're thinking of deploying this out in different parts of the world. And when we got an image that showed how X-rays are read in this hospital that we're working with in Africa, this is what we saw. And so the idea that one could snap a picture and upload it and get a diagnosis seems very powerful. So the third case study I want to take you through is being able to look at MR. So we've talked about a 1D setup where we had an ECG signal. We've talked about a 2D setup with an X-ray. How many of you are thinking of working on a 3D problem for your project? Okay. A few. Oh, that's good. Cool. So here we looked at knee MR. So MR of the knee is the standard of care to evaluate knee disorders. And more MR examinations are performed on the knee than any other part of the body. And the question that we sought out to answer was, can we identify knee abnormalities? Two of the most common ones include an ACL tear and a meniscal tear at the level of radiologists. Now with the 3D problem, one thing that we have that we don't have in a 2D setting is the ability to look at the same thing from different angles. And so when radiologists do this diagnosis, they look at three views: the sagittal, the coronal, and the axial, which are 3 ways of looking through the 3D structure of the knee. And in an MR, you get different types of series based on the magnetic fields. And so here are 3 different series that are used. And what we're going to do is output for a particular knee MR examination the probability that it's abnormal, the probability of an ACL tear, and the probability of a meniscal tear. Important thing to recognize here is this is not a multi-class problem in that I could have both types of tears. It's a multi-label problem. So we're going to train a convolutional neural network for every view pathology pair. So that's 9 convolutional networks, and then combine them together using a logistic regression. So here's what each convolutional neural network looks like. I have a bunch of slices within a view. I'm going to pass each of them to a feature extractor. I'm going to get an output probability. So we had 1,400 knee MR exams from the Stanford Medical Center, and we tested on 120 of them, where the majority vote of 3 subspecialty radiologists established the ground truth. And we found that we did pretty well on the 3 tasks and had the model be able to pick up the different abnormalities pretty well. And one can extend these methods of interpretability to 3D inputs as well. So that's what we did here. Okay, so I saw this cartoon a few weeks ago, and I thought it's pretty funny, which is a lot of machine learning engineers think that they don't need to externally validate, which is find out how my model works on data that's not where my original data set came from. So there's a difference in distributions, but it's really quite exciting when a model does generalize to data sets that it's not seen before. And so we got this data set that's public from a hospital in Croatia. And here's how it was different. So it was a different kind of series, so different magnetic properties. It was a different scanner, and it was a different institution in a different country. And we asked, okay, what happens when we run this model off the shelf that was trained on Stanford data, but tested on that kind of data? And we found that it did relatively well without any training at all. But then when we trained on it, we found that we were able to outperform the previously best reported result on the data set. So there's still some work to be done in being able to generalize sort of my network here that was trained on my data to be able to work on data sets from different institutions, different countries as well. But we're making some steps along that way. Remains a very open problem for taking.
Images acquired by in hospital that have some sort of uniformity.
Yeah, so we did the best we could in terms of processing. So one of the pre-processing steps that's important is being able to get the mean of the input data to be as close to the mean of the input data that you trained on. So that was one pre-processing step we tried, but we were trying to minimize that to say, out of the box, how would this work? If we had never seen this data before, how would it work on that population? So one big topic across a lot of applied fields is asking the question, okay, we're talking about models working automatically, autonomously. How would these models work when working together with experts in different fields? And here we ask that questions about radiologists and about imaging models. would it be possible to be able to boost the performance if the model and the radiologist work together? And so that's really the setup. A radiologist with model, is that better than the radiologist by themselves? And here's how we set it up. We said, let's have experts read the same case twice, separated by a certain set of weeks, and then see how they would perform on the same set of cases. And what we found that we were able to increase the performance generally with a significant increase in specificity for ACL tears. That means if a patient came in without an ACL tear, I'd be able to find it better. So in the future, yes, question?
Wouldn't that kind of bias the opinion of the radiologist, or is that the intended thing that you want to kind of bias his opinion before he actually looks at the image itself?
Yeah, so that's a good question, and I think sort of automation bias captures a lot of this in that once we have sort of models working with experts together, can we expect that the experts will sort of take it less seriously? Because that's a big concern, and start relying on what the model says and says, I won't even look at this exam, I'm just going to trust what the model says blindly. That's absolutely possible in a very open area of research. Some of the ways that people have tried to address it is to say, you know what I'm going to do from time to time, I'm going to pass in an exam to the radiologist for which I'm going to flip the answer. And I'll know the right one. And if they get that wrong, I'll alert them that you're relying too much on the model. Stop. But there are a lot of more sophisticated ways to go about addressing automated bias. And as far as I know, it's a very open field of research, especially as we're getting into deep learning assistants. And one utility of this is to say, basically, that these set of patients don't need follow-up. Let's not send them for unnecessary surgery. Great. So I shared 3 case studies from the lab. The final thing I want to do is to talk a little bit about how you can get involved if you're interested in applications of AI to healthcare. So the first is the ability for you to just get your hands dirty with data sets and be able to try out your own model. So we have, from our lab, released the Mura data set, which is a large data set of bone x-rays, and the task is to be able to tell if the x-rays are normal or not, and they come from different parts of the upper body. And that's what the data set x-rays look like. And this is a pretty interesting setup because you have more than one view, so more than one angle for the same body part, for the same study, for the same patient. And the goal is to be able to combine these well into convolutional neural network and be able to output the probability of abnormality. And one of the interesting things here for transfer learning as well is, do you want to train the models differently per body part, or do you want to train the same model for body parts, or combine certain models? So a lot of design decisions there. And this is what some trained models look like. This is a model baseline that we released that's able to identify a fracture here and a piece of hardware on the right. And you can download the data set off our website. So if you Google Mura dataset or go on our website, stanfordmlgroup.github.io, you should be able to find it. The second way to get involved is through the AI for Healthcare Bootcamp, which is a 2-quarter-long program that our lab runs, which provides students coming out of classes like 230 an opportunity to get involved in research. And here, students receive training from PhD students in the lab and medical school faculty. to work on structured projects over 2 quarters. And if you have a background in sort of AI, which you do, then you're encouraged to apply. And we're working on a wide set of problems across radiology, EHR, public health, and pathology right now. This is what the lab looks like. We have a lot of fun. And the applications for the bootcamp starting in the winter are now open. So the early applications deadline is November 23rd. And you can go on this link and apply. So that's my time. Thank you so much for having me, and thanks for having me, Kian. Thank you.
Do you want to take 1 or 2 questions?
Yes, I'll take a couple questions.
Somebody already asked a question about privacy concerns. In terms of other ethics concerns, what about compensation for the medical experts that you're potentially putting out of business with a free tool, like the one that you're developing, or just in general? Because their knowledge is being used to train these models. It's not free.
Mm-hmm. Yeah. So the question was, we're having these automated AI models trained with the knowledge of medical experts. What are ways in which we're thinking of compensating these medical experts right now or in the future when we have possibly automated models? I think a lot of people are thinking about these problems and working on them right now. There are a variety of approaches that people are thinking about in terms of economic incentives, and there's a lot of fear about sort of will AI actually work with or augment experts in whatever field they're working on. I don't have a great silver bullet for this, but I know there's a lot of work going on in there.
I just wanted to know, when you're looking through MRIs which are looking at 4 or 5 category of tissues, like you listed there, one of them is the most likely. It's possible that a human looking at it could point out something that was not being looked at by the AI model at that time.
Yeah.
So how do you address that?
Yeah, that's a great question. So just to repeat the question, it's we're looking at MR exams, and we're saying for these 3 pathologies, we're able to output the probabilities. What happens if there's another pathology that we haven't looked at? So I have a couple of answers for that. The first is that one of the categories here was simply to tell whether it was normal or abnormal. So the idea here is that the abnormality class will capture a lot of different pathologies there, at least the ones seen at Stanford. But it's often the case that we're building for one particular pathology, and then there's obviously a burden on the model and the model developers to be able to convey, hey, look, our algorithm model only does this, and you really need to watch out for everything else that the model doesn't cover. Maybe that's unless there's one more question? No. All right, that's the last question we'll take then. Thank you once again.
So now you've got the perspective. Is the microphone working? Yeah. Now you've got the perspective of an AI researcher working in healthcare. Now you're going to be the AI researcher working in healthcare. We're going to go over a case study that is targeted at skin disease. So, in order to detect skin disease, sometimes you take pictures, microscopic pictures of cells on your skin and then analyze those pictures. So that's what we're going to talk about today. So let me talk about the problem statement. You're a deep learning engineer and you've been chosen by a group of healthcare practitioners to determine which part of a microscopic image corresponds to a cell. Okay, so here's how it looks like. On the black and white, it's not a black and white image, it's a color image, but it looks black and white. The input image is the one that is closer to me. And the yellow one is the ground truth that has been labeled by a doctor, let's say. So what you're trying to do is to segment the cells on this image. And we didn't talk about segmentation yet, or a little bit. Segmentation is about producing a value, a class for each of the pixels on our image. So in this case, each pixel would correspond to either no cell or cell, 0 or 1. And once we output a matrix of zeros and ones telling us which pixels corresponded to a cell, we should get hopefully a mask like the yellow mask that I overlapped with the input image. Does that make sense? Yeah.
Isn't there a third category that's the boundary? Because in the colored image, the yellow one, you don't have the boundary as part of the cell.
Yeah, we'll talk about the boundary later. But right now, assume it's a binary segmentation, so 0 and 1, no cell and cell. Okay? So, it's going to be very interactive, and I think we're going to use Menti for several questions and group you guys into groups of 3. So here are other examples of images that were segmented with a mask. Now, doctors have collected 100,000 images coming from microscopes, but the images come from 3 different microscopes. There is a type A, type B, and type C microscope. And the data is split between these 3 as 50% for type A, 25% for type B, 25% for type C. The first question I'll have for you is, given that the doctors want to be able to use your algorithm on images from the microscope of type C. This microscope is the latest one. It's the one that is going to be used widely in the field. And they want your network to work on this one. How would you split your data set into train, dev, and test set? That's the question. And please group in teams of 2 or 3 and discuss it for a minute on how you would split this data set. Thanks. Yeah, thanks. You can start going on Menti and write down your answers as well. Okay. So take 30 seconds to input your insights on Menti. You can do 1 per team. And we'll start going over some of the answers here. Okay. Dev test, split C, train on A plus B, 20K in train, 2.5 in dev and test. Training 80, all A, all B, 5K C, dev 10K C, test 10K C. 95.5 where test and dev is from population we care about. I think these are good answers. I think there is no perfect answer to that, but 2 things to take into consideration. You have a lot of data, so you probably want to split it into 95.5, closer to that than to 60-20-20. And most importantly, you want to have C images in the test, dev and test set to have the same distribution among these 2. That's what you've seen in the 3rd course. And we would prefer to have actually C images in the train set. You want your algorithm to have seen C images. So I would say a very good answer is this one, 95.5, where the 5 and 5 are exclusively from C. And you also have C images in the 90% of train images. Any other insights on that? Everybody agrees? Yeah.
How do we detect that like Microscope's A and B data set doesn't have some like hidden, features that will mess up the training?
Yeah. So there is much more thing we didn't talk about here. One is how do we know what's the distribution of microscope A images and microscope B images versus microscope C? Do they look like each other? If they do, all good. If they don't, how can we make sure the model doesn't get bad hints from these two distributions? Another thing is data augmentation. We could augment this data set as well and try to get as much as C distribution images as possible. We're going to talk about that. Okay. Split has to roughly be 95/5, not 60/20/20. Distribution of dev and test sets has to be the same, contain images from C, and there should also be C images in the training set. Now talking about data augmentation. Do you think you can augment this data? And if yes, give only 3 distinct methods you would use. If no, explain why you cannot. You want to take 30 seconds to talk about it with your neighbors? Yeah. Okay. Okay, guys. Let's go over some of the answers. So rotation, zoom, blur. I think looking at the images that we have from the cells, this might work very well. Rotation, zoom, blur, translation, combination of those, stretch, symmetry, like probably a lot of those work. One follow-up question that I'll have is, can someone give an example of a task where data augmentation might hurt the model rather than helping it? Yeah.
Going to overfit on the test set?
If you want to overfit on the test set, can you be more precise?
Like, then you don't want it to generalize too much.
Oh, you don't want your model to generalize too much. Okay. Yeah, there's some cases where you don't want the model to generalize too much, especially in autoencoder. But any other ideas?
If you're doing like face detection, you wouldn't want the face to be like upside down or like either side.
I see. So if you do face detection, you probably don't want the face to be upside down, although we never know depending on the use. But it's not going to help much if the camera is always like that and it's filming humans that are not upside down. But I don't think it's going to hurt the model. It's probably going to not help the model, I guess. Yeah?
Anything doing distance detection, if you like stretch the image, then
good point.
It's accurate.
So there are algorithms like maybe FlowNet. It's an algorithm that's used for on videos to detect the speed of a car, let's say. If you stretch the images, probably you cannot detect the speed of the car anymore. Any other examples? Yeah. Character recognition, I think it's a good example. So let's say you're trying to detect what this is and you do symmetry flip and you get that. Like you're labeling as B everything that was D and as D everything that was B. For 9 and 6, it's the same story. So these data augmentations are actually hurting the model. because you don't relabel when you augment your data, all right? Okay. Okay, so yeah, many augmentation methods are possible: cropping, adding random noise, changing contrast. I think data augmentation is super important. I remember a story of a company that was working on self-driving cars and also virtual assistants in cars. You know, like this type of interaction you have with someone in your car, a virtual assistant. And they noticed that the speech recognition system was actually not working well when the car was going backwards. Like, no idea why. Like, why? It doesn't seem related to the speech recognition system of the car. And they tested out, and they looked, and they figured out that people were putting their hands in the passenger seat, looking back and talking to the virtual assistant. And because the microphone was in the front, the voice was very different when you were talking to the back of the car rather than the front of the car. And so they used data augmentation in order to augment their current data. They didn't have data on that type of people talking to the back of the car. So by augmenting smartly, you can change the voices so that they look like they were used by someone who was talking to the back of the car, and then solve the problem. Okay. Small question, we can do it quickly. What is the mathematical relation between nx and ny? So remember, we have an RGB image, and we can flatten it into a vector of size nx, and the output is a mask of size ny. What's the relationship between nx and ny? Someone wants to go for it? They're
equal.
They're equal? Who thinks they're equal? Who thinks they're not equal, and why?
3:1 because you have RGB on this side and then you just have one color or
Exactly.
color on the other.
ny will be 3 nx. Nx will be 3 and y because you have RGB images. And for each RGB pixel, you would have one output, 0 or 1. Okay, that was a question on one of the midterms. It was a complicated question. What's the last activation of your network? Sigmoid. You want probably an output 0 and 1. And if you had several classes, so later on we will see, we can also segment per DCs, then you would have a softmax. What loss function should we use? I'm going to give it to you to go quickly because we don't have too much time. You're going to use a binary cross-entropy loss over all the output, the entries of the outputs of your network. Does that make sense? So always thinking through the loss function is interesting. Okay, so you have a first try and you've coded your own neural network that you've named model M1, and you've trained it for 1,000 epochs. It doesn't end up performing well, so it looks like that. You give it the input image through the model and get an output that is expected to be the following one, but it's not. So one of your friends tells you about transfer learning, and they tell you about another labeled data set of 1 million microscope images that have been labeled for skin disease classification, which are very similar to those you want to work with from microscope C. So a model M2 has already been trained by another research lab on this new data set on a 10-class disease classification. And so here is an example of input-output of the model. You have an input image that probably looks very similar to the ones you're working on. The network has a certain number of layers and a softmax classification at the end that gives you the probability distribution over the disease that seems to correspond to this image. So they're not doing segmentation anymore, right? They're doing classification. Okay, so the question here is going to be, you want to perform transfer learning from M2 to M1. What are the hyperparameters that you will have to tune? It's more difficult than it looks like, so think about it, discuss with your neighbors for a minute. Try to figure out what are the hyperparameters involved in this transfer learning process. Okay, take 15 more seconds to wrap it up. Okay. Let's see what you guys have. Learning rate, it is a hyperparameter. I don't know if it's specific to the transfer learning. Weights of the last layers. So I don't think that's a hyperparameter. Weights are parameters. New cost function for additional output layers. I think that's the choice of the loss, you might count it as a hyperparameter. I don't think it's specifically related to transfer learning. You will have to train with the loss you've used on your model M1. Number of new layers, yeah. Weights of the new, not a hyperparameter. Okay, last one or two hidden layers of M2. So do we train, what do we fine tune? It's a lot about layers actually. Size of added layers. Not sure. Okay, let's go over it together because it seems that there's a lot of different answers here. Let me try to write it down here. So let's say we have the model M2. Is it big enough for the back? We have the model M2, and so we give it an input image. Okay, input. And the model M2 gives us a probability distribution, softmax. So we have a softmax here. You will agree that we probably don't need the softmax layer. We don't want it, we want to do segmentation. So one thing we have to choose is how much of this pre-trained network, because it's a pre-trained network, how much of this network do we keep? Let's say we keep these layers, because they probably know the inherent salient features of the data set, like the edges of the cells that we're very interested in. So we take it. So we have it here. And you agree that here we have a first hyperparameter, that is L, the number of layers from M2 that we take. Now, what other hyperparameters do we have to choose? This is L. We probably have to add a certain number of layers here in order to produce our segmentation. So there's probably another hyperparameter, which is L0. How many layers do I stack on top of this one? And remember, these layers are pre-trained, but these ones are randomly initialized. That makes sense? So two hyperparameters. Anyone sees the third one? The third one comes when you decide to train this new network. You have the input image, give it to the network, get the output segmentation mask. Segmentation mask, let's say seg mask. And what you have to decide is how many of these layers will I freeze? How many of the pre-trained layers I freeze? Probably if you have a small data set, you'd prefer keeping the features that are here, freezing them, and focusing on retraining the last few layers. So there is another hyperparameter, which is how much of this will I freeze, LF. What does it mean to freeze? It means during training, I don't train these layers. I assume that they've been seeing a lot of data already. They understand very well the edges and the less complex features of the data. I'm going to use my small data set to train the last layers. So 3 hyperparameters. L, L0, and LF. Does that make sense? Okay, so this is for transfer learning. So it looks more complicated than the question was more complicated than it looked like. Okay, let's move. Where am I? Okay, let's go over another question now. Okay, so this we did it. Now it's interesting because here we have an input image, and in the middle we have the output that the doctor would like. But on the right, you have the output of your algorithm. So you see that there is a difference between what they want and what we're producing. And it goes back to someone mentioned it earlier. There is a problem here. How do you think you can correct the model and or the data set to satisfy the doctor's request? So the issue with this image is that they want to be able to separate the cells among them, and they cannot do it based on your algorithm. It's still a little hard. There's something to add. So can someone come up with the answer? Or do you want to explain, actually, you mentioned one of the answers so that we can finish the slide, yeah?
You want to add boundaries, because now it looks like you could have like 3 cells on the bottom left blurring in together. And so if you start adding boundaries, it makes the cells more well-defined.
Good answer. So one way is when you label your data sets. Originally, you labeled with 0s and 1s for every pixel. Now, instead, you will label with 3 classes. 0, 1, or boundary. Like, let's say 0, 1, 2 for boundary. Or even the best method, I would say, is that for each pixel, for each input pixel, the output will be the corresponding, okay, this one is not good, the corresponding label. Like this is a cell picture, P of cell, P of boundary, and P of no cell. What you will do is that instead of having a sigmoid activation, you will use a softmax activation, okay? And the softmax will be for a pixel. One other way to do that, if it still doesn't work even if you label the boundaries. What is another way to do that? You relabel your data sets by taking into account the boundaries. The model still doesn't perform well. I think it's all about the weighting of the loss function. It's likely that the number of pixels that are boundaries are going to be fewer than the number of pixels that are cells or no cells. So the network will be biased towards predicting cell or no cell. Instead, what you can do is, when you compute your loss function should have 3 terms. 1 binary cross entropy, let's say, for no cell, 1 for cell, and 1 for boundary. Okay? And this is going to be summed over I equals 1 to ni. The whole output pixel values. What you can do is to attribute a coefficient to each of those, alpha, beta, or 1. And by tweaking this coefficient, if you put a very high, a very low number here and there, it means you're telling your model to focus on the boundary. You're telling the model that if you miss the boundary, it's a huge penalty. We want you to train by figuring out all the boundaries. That's another trick that you could use. One question on that, yeah?
When you say you're relabeling your data set, you also you do that manually, or is that a suggestion?
Good question. What do I mean by relabeling your data set? This last Friday section, you've been labeling bounding boxes, for the YOLO algorithm. So the same tools are available for segmentation, where you have an image and you would draw the different lines. In practice, if the tool that you were using, the line used will just count as a cell, everything including the line with everything inside what you draw, plus the boundary would count as cell and the rest as no cell. It's just a line of code to make it different. The line you drew will count as boundary, everything inside will count as cell, and everything outside will count as no cell. So it's the way you use your labeling tool. That's all.
So do we make alpha and beta static, or do we make alpha and beta learnable parameters, like we stick another neural network in between?
I think it's not learnable parameters. It's more hyperparameters to tune. So the same way you tune lambda for your regularization, you would tune alpha and beta.
So when do you make a distinction, like if that becomes an attention mechanism, how do you combine those different?
So this is not an attention mechanism because it's just a training trick, I would say. You cannot know how much attention will tell you for each image how much the model is looking at this part versus that part. This is not going to tell you that. It's just a training trick.
What's the advantage to doing it this way as opposed to like object detection, like detecting each cell, putting a bounding box?
So the question is, what's the advantage of doing segmentation rather than detection?
Yeah.
Yeah, so detection means you want to output a bounding box. If you output a bounding box, what you could do is output the bounding box, crop it out, and then analyze the cell and try to find the contour of the cell. But if you want to separate the cells, if you want to be very precise, segmentation is going to work well. If you want to be very fast, bounding boxes would work better. I think that's the general way. Segmentation is not working as fast as the YOLO algorithm works for object detection. Yeah, I would say that. But it's much more precise. Okay. So modify the data set in order to label the boundaries. On top of that, you can change the loss function to give more weights to boundaries or penalize false positives. Okay. We have one more slide, I think. So let's go over it. So now the doctors, they give you a new data set that contain images similar to the previous ones. The difference is that each image now is labeled with 0 and 1. 0 meaning there are no cancer cells on that image, and 1 means there is at least a cancer cell on this image. So we're not doing segmentation anymore. It's a binary classification. Image, cancer, or no cancer. Okay? So you easily build a state-of-the-art model because you're a very strong person in classification, and you achieve 99% accuracy. The doctors are super happy, and they ask you to explain the network's prediction. So given an image classified as 1, how can you figure out based on which cell the model predicts 1? So Pranav talked a little bit about that. There are other methods that you should be able to figure out right now, even if you don't know class activation maps. So to sum it up, we have an image, input image, put it in your new network that is a binary classifier. And the network says 1. You want to figure out why the network says 1, based on which pixels. What do you do?
Visualize the weights.
Visualize the weights. What do you visualize in the weights?
The edges.
So I think visualizing the weights is not related to the input. The weights are not going to change based on the input. So here you want to know why this input led to 1. So it's not about the weights.
Do numerical gradients on each pixel of the input and see which one impacts output?
Good idea. So you know, after you get the 1 here, this is y hat. Basically, it's not exactly 1. Let's say it's 0.7 probability. What you can remember is that this number, derivative of y hat with respect to x, is what? It's a matrix of shape same as x. You know, it's a matrix. And each entry of the matrix is telling you how much moving this pixel influences y hat. You agree? So the top left number here is telling you how much x1 is impacting y hat. Is it or not? Maybe it's not. If you have a cat detector and the cat is here, you can change this pixel, it's never going to change anything. So the value here is going to be very small, closer to 0. Let's assume the cancer cell is here. You will see high number in this part of the matrix. Because these are the pixels that if we move them, it will change y hat. Does it make sense? It's a quick way to interpret your network. It's not too good, like you're not going to have tremendous results, but you should see these pixels have higher derivative values than the others. Okay, that's one way. And then we will see in 2 weeks how to interpret neural networks, visualizing the weights included and all the other methods. Okay, so gradient with respect to it. Your model detects cancer cells from the test set images with 99% accuracy, while a doctor would on average perform 97% on the same task. Is this possible or not? Who thinks it's possible to have a network that achieves more accuracy on the test set than the doctor? Okay, can someone say why? You have an explanation?
You can look at complex things that possibly you couldn't get from user training.
Okay, the network probably looks at complex things that doctor didn't see. That's what you're saying? Possibly? I think there's a more rigorous explanation.
Human error is an approximation for Bayes error, but we don't actually know what it is, so theoretically you can get better.
Yeah, so here we're talking about Bayes error, human level performance, and all that stuff. That's when you should see it. So one thing is that there are many concepts that you will see in course 3 that are actually implemented in the industry, but it's not because you know them that you're going to understand that it's time to use them. And that's what we want you to get to. Like now, when I ask you this question, you have to think about Bayes error, human level accuracy, and so on. So the question that you should ask here is, what was the data set labeled? What were the labels coming from? If the data set was labeled by individual doctors, I think that looks weird. Like, if it was labeled by individual doctors, I think it's very weird that the model performs better on the test set than what doctors have labeled. Simply because the labels are wrong. 3% of the time, on average, the labels are wrong. So you're teaching wrong things to your model 3% of the time. So it's surprising that it gets better. It could happen, but surprising. But if every single image of the dataset has been labeled by a group of doctors, as Pranav talked about it, then the average accuracy of this group of doctors is probably higher than one doctor. Maybe it's 99%, in which case it makes sense that the model can beat one doctor. Does it make sense? So you have Bayes error, you're trying to approximate with like the best error you can achieve. So grouping a cluster of doctors, probably better than one doctor. This is your human level performance, and then you should be able to beat one doctor. It's an idea. Okay. So you want to build a pipeline that goes from image taken by the front of your car to steering direction for autonomous driving. What you could do is that you could send this image to a car detector that detects all the cars, a pedestrian detector that detects all the pedestrians, and then you can give it to a path planner, let's say, that plans the path and outputs the steering direction, let's say. So it's not end-to-end. End-to-end would be, I have an input image and I give it, I want this output. So a few other disadvantages of this is something can go wrong anywhere in the model. You know, how do you know which part of the model went wrong? Can you tell me which part? I give you an image, the steering direction is wrong. Why? Yeah.
Look at the different components to try to isolate those.
Good idea. Looking at the different components. So what you can do is look what happens here and there. Look what's happening here and there. Do you think based on this image the car detector worked well or not? You can check it out. Do you think the pedestrian detector worked well or not? You can check it out. If there is something wrong here, it's probably one of these two items. It doesn't mean this one is good. It just means that these two items are wrong. How do you check that this one is good? You can label ground truth images and give them here as input to this one and figure out if it's figuring out the steering direction or not. If it is, it seems that the path planner is working well. If it is not, it means there's a problem here. Now, what if every single component seemed to work properly? Like let's say these two work properly, but there's still a problem. It might be because what you selected as a human was wrong. The path planner cannot get the steering direction correct based on only the pedestrians and the car detection and the cars. Probably need the stop signs and stuff like that as well. You know, and so because you made hand engineering choices here, your model might go wrong. That's another thing. Another advantage of this type of pipeline is that data is probably easier to find out for every algorithm rather than the whole end-to-end pipeline. If you want to collect data for the entire pipeline, you would need to take a car, put a camera in the front, like build a kind of steering wheel angle detector that will measure your steering wheel at every step while you're driving. So you need to drive everywhere, basically, with a car that has this feature. It's pretty hard. You need a lot of data, a lot of roads. While this one, you can collect data of images anywhere and label the pedestrians on it. You can detect cars by the same process. Okay? So these choices also depend on what data can you access easily or what data is harder to acquire. Any questions on that? You're going to learn about convolutional neural networks now. You're going to get fun with a lot of imaging. You have a quiz and 2 programming assignments for the first module. Second module, same. Midterm next Friday, not this one. Everything up to C4M2 will be included in the midterm. So up to the videos you're watching this week. Includes TA sections and next one, and every in-class lecture, including next Wednesdays. And this Friday you have a TA section. Any questions on that? Okay, see you next week, guys.